And the topic refers to Himalaya, as you can see, but it reflects my inspiration of that mountains. And but it's not the main topic in my talk. So, as everybody knows, we have three parameters in physics, especially in cosmology. For example, we have cosmological constant, which has to be fitted to measurement and gets a very tiny value, 10 to minus 29 grams per centimeter to third. We have problem to calculate that value from any more theoretical model. We just simply have to fit to the experimental value. And another free parameter in cosmology is in the Starobinsky model, which is not forbidden in the Planck mission. It is allowed, and one of the best model describing inflation. And we have two equivalent formulations of that model, which is one given with the presence of Inflaton field, and another without. It is simply that they are connected by rescaling of that field, and this R includes also that rescaling, conformal rescaling. But they are completely equivalent. And we have here A and alpha as a free parameters. Another so-called parameters or free parameters which we have to fit to experiments is the rate of inflation, which means the number of efforts, and duration of inflation, and the tensor scalar ratio, and some other. In the standard model of particle physics, we know there are 18 free parameters in standard model, and taking into account extension by masses in neutrino, we can calculate together around 25 free parameters. Especially the masses of elementary particles are things which we don't know how to predict them from calculations. So we simply don't know first principles allowing for derivation of these free parameters in cosmology and in particle physics. That's the reason we have to turn to the wisdom of Himalaya. So let me start to develop this sentence. Our strategy is the following. We are taking space-time M, and we try to embed this space-time into some broader manifold, which is K here, and we try to draw some conclusions from that embedding. And we require that K is a compact, smooth form manifolds. All loops are contractible, and there exists the background geometry, which means this K manifold should be Ricci flat. Yao showed in '78 that there exists only one topologically such a manifold fulfilling these three conditions, and this is a K3 surface. But the K3 surface, as it is not sufficient to draw any interesting conclusions. We are mainly interested in smooth structure of this surface. And this is the rest of my talk devoted to describing that this smooth structure. And also this is the explanation of the Himalaya, referring to Himalaya in this talk, because K3 was chosen in relation to the famous K2 peak, of course, but also are the first Kumelko-Daira and Chern. It's a citation from Weil. So.
You are embedding space-time, which is topology R4, into a four-dimensional compact manifold.
Yes.
So this is basically a compactification of R4. No?
It's not a compactification, it's just embedding. It's not a compactification in the sense of just embedding. You can do that, but I don't know what it means. I don't have any results from that embedding. Embedding in S4 is different because it is R4 is a dense subset. Here we don't say anything about density of that space-time embedding. We just take any manifold which we like and embed as an open subset of that manifold our space-time. That's all. It's not dense. That's the distinction. Yeah. So K3 surface is a special case of Calabi-Yau manifold known in superstring theory. In complex dimension 3, we have in fact hundreds of such known examples of this Calabi-Yau manifolds, which parameterizes four-dimensional vacua of string theory. Our main interest is two-dimensional case, where you can see there exists the only one non-trivial Calabi-Yau manifold, which is precisely the K3 surface. T4 is also Calabi-Yau, but it is completely flat. But K3 is non-trivial in the sense that scalar tensor is non-zero, but is Ricci flat. By the way, nobody knows any explicit Ricci flat metric on any non-trivial Calabi-Yau in complex dimensions 2 and 3. So on K3 surface also we don't know any such explicit example. So what about exotic K3? As many others real four-dimensional manifolds, K3 surface also carry infinite many pairwise non-diffeomorphic smooth structures, which means that every such manifold with such a smooth structure is homomorphic to K3 surface, but they are not diffeomorphic pairwise. The question is which such smooth K3 is favored by physics, and how we can determine this smoothness structure. It is quite non-trivial question, but it can be very effectively performed. The answer to the question can be done. In the process of doing that, we will need homology tree spheres, especially Brieskorn tree spheres. Homology tree spheres are three manifolds, three-dimensional real manifolds, which have the same homologies as tree sphere above including one, and have such, for example, three-dimensional homology spheres have such homologies as here. It doesn't mean that such a sigma, such a homology tree sphere has to be simply connected. From Hurewicz theorem, we know that in fact it is not necessary, and but the fundamental group has to be perfect. And the famous example is the Poincaré tree sphere, which in terms of Brieskorn description is written like that. In general, any Brieskorn sphere refers to three pairwise prime integers, and they fulfill such equations. Our main difference, our main concern here is the difference between ordinary tree sphere and this homology sigma 2, 5, 7, sphere. I will explain why. So how to describe exotic K3 structure? From topological results, we know that there exists such a compact, constructive, smooth submanifold, three-dimensional submanifold, four-dimensional submanifold, which has a boundary which is three-dimensional, of course. And this Agbulut cork determines, it is called Agbulut cork, and it determines a smooth structure by simply cutting out A and regluing it together with the change by some involution. We know also that the boundary of Agbulut cork in one case is our homology tree sphere sigma 2, 5, 7. This geometry, this is hyperbolic manifold with negative curvature, scalar curvature. The point is that given exotic smooth structure on K3 surface, we cannot replace sigma 2, 5, 7 by ordinary tree sphere. Simply, such a sphere does not exist inside our K3 surface. The point of that construction is the following. We have K3 here. Here is Agbulut cork. Here is the boundary of the Agbulut cork, which is sigma 2, 5, 7. And inside the cork, we can find a smoothly embedded tree sphere. But outside, we cannot. And at the boundary of this process, we found the homology tree sphere. And the main point for us is to find smooth transition from this S3 to this sigma 2, 5, 7 Briscoe sphere, and this transition is given by smoothly embedded cobordism. So such a cobordism is a four-dimensional manifold with a boundary which is on one side. Let's use this order is S3. In the other side, we have sigma 2, 5, 7. And this manifold is a four-dimensional cobordism. And this cobordism can be, in fact, smoothly embedded somewhere here. And we are describing the conclusion, the fact that we can smoothly embed such cobordism in this K3 surface using Agbulut cork. And the point is, we cannot replace, starting from tree sphere, we cannot end on the tree sphere here. It has to be homology tree sphere. So what to do in order to build such a smooth cobordism? We have to glue some kinky handlings in the terminology of Friedman, which are also called Caisson handles. There are, in fact, infinite stages geometric construction. Let's use abbreviation Caisson hand as CH, and it is related to ordinary two-hand. Two-hand is something like such a four-dimensional manifold, plus boundary S2, R2. Friedman showed that this is in fact, but Caisson handle is infinite geometric construction, which can be very complicated, and in fact, it goes from attempt to discard such intersection where this line shows two-dimensional surfaces embedded in four-dimensional manifold. When we want to replace such multiple intersections, we just glue in some disk and smoothly slide this line here such that at the end they become separated. But this disk is not necessary that such a disk exists in every case. And it can happen that when we glue such a disk, they can intersect itself. So there appear many self-intersections, like something here. And we need to glue in another disk. But this another disk produces also maybe many other self-intersections. And to avoid these self-intersections, we glue in another disk, another. And Friedman's idea was to extend this procedure up to infinity. And with big surprise, he proved that such infinite construction is the same as this two-handle, topologically the same, but not smoothly the same. And this is the point of where smooth structure can appear in four-dimensional manifolds. So what we are doing from physical point of view with this cobordism, and when we glue in such infinite Kazon handle, we calculate some contribution coming from first stage, second stage, n stage up to infinity. And at every stage, the contribution looks, at n stage, the contribution looks like this. And when we sum, and the theta is in fact the theta is in fact depicted here. This is theta. And this exponential term comes from simply summing over stages of the Kazon handle. And next, what we are doing, we are using Chern-Simons invariant of our homology tree sphere, and it can be shown. It is a theorem that this theta contribution from level of the Kazon hand can be written as in terms of Chern-Simons invariant of our homology tree sphere. And so the theta is precisely of that form. And from that, we get a kind of exponential expansion. Next, we are taking this radius of the tree sphere. We are taking as a Planck length of order of the Planck length, and we are checking what we are getting at the end after such expansion. And it is some surprise because the results are quite physical. Starting from the Planck length, we get something which is this length, and the efforts used here, which are calculated as a purely topological, in a purely topological invariant manner, gives us 51, which is a cosmologically relevant number. So the n can be given in such a form. It's simple. Logarithm of a pi comes from Chern-Simons invariant. It's a simple formula, but it's the number of efforts is physically relevant, which so we infer that such a topological change, smoothly encoded in our K3 surface, can refer somehow to can model inflational expansion of our universe. And this is, in fact, the presence of Agbolud quark which does it. So, we have first indication that something can happen in such a model. But we are taking a more careful analysis of the topology involved here. And in the K3 surface can be represented in such decomposition. It is quite old formula. And here is the manifold which corresponds to the direct sum of whose intersection form is represented by direct sum of two 8x8 exceptional matrices. And here we have a connected sum of three such manifolds. And altogether, topologically, we can decompose K3 surface into such pieces. And what we know from general ground, the manifold corresponding to one such E8 exceptional matrix has boundary which is the Poincare sphere. The sum of this, the manifold corresponding to the sum of this direct sum of these matrices cannot be realized as a smooth closed form manifold. It follows from Donaldson theorem. And moreover, it has the boundary, which is the connected sum of two Poincare spheres. Everything happens inside the K3 surface. And so we have first, we had first transition, now we have the second transition. And from the Briscoe sphere, we are ending at the sum of two Poincare spheres. To get this transition to be smooth, again, we have to glue in three Caisson handles. So this step essentially involves gluing three Caisson handles. And next, our move is to determine energy scales corresponding to the first topology change and to the second topology change. How is it done? At the first topology change, we calculate the energy of such a change is calculated by this expression. It is simply Planck energy corresponding to the radius Planck length sphere, three-sphere at the beginning. And here are contribution coming from three stages of the Caisson hand. Why three stages? Because there is a theorem of Friedman showing that it is you can embed any Caisson hand can be embedded in three stages, but you cannot take less. We are interested in the minimal time or energy scale available smoothly in our model. So the minimally you have to take three stages of the Caisson hand, and because of the three stages we have 0, 1, 2, 3. You have this expression. And it gives more or less the good energy, which is quite physically. And the transition time is also physically. So, but again, our calculation is purely topological. Remind that theta was just a simple expression function of Chern-Simons invariant of our sigma. Oh, it's here. Theta is here. So it's purely topological. Okay, let's see what can we do next. Okay. Now we turn to the second energy scale assigned to the second transition, and we have the following expression. It is simply the first energy transition multiplied by full contribution from infinite Caisson hand. Only that. And what we get energy level, which is also physical, which is less than Electroweak scale. It's 63 GeV. So second energy scale, which is close to Electroweak scale, is also topologically supported, and it is derived only because of the exotic smooth structure of K3 surface. Okay. What can we say about masses of neutrinos? Just we implement seesaw mechanics, which is known from standard model calculations, and we are using the simplest case, such a matrix where M is much less energy scale than B, and lambda 1, lambda 2 are two eigenvalues of such a matrix. And we insert as M our second energy scale, as B first energy scale. After simple calculation, we get such expression for neutrino mass. We know from Planck mission the upper bound for the sum of all three neutrinos, which fit well with our purely topological calculation. Okay. What about in the seesaw mechanics? We need right and left-handed neutrinos. And what about this story? After this is coded into Dirac operators. Simply, mapping class group of our homology tree sphere is non-trivial. It is two elements. And you can, one can assign two Dirac operators to such things, which means we can assign two left and right-handed Dirac operators and neutrinos coming from that fact. After second topology change, which give us at the Electroweak energy scale, the mapping class group of the Poincare sphere is trivial. So which means that we are left with a single left-handed neutrino, what is required by physical model. So, okay. But it can be done by precise calculations. It is not just the rough observation of topology. Just we have written down that expressions, and it is quite surprise to us. What about cosmological constant value? The formula for cosmological constant value is given here. It's also, as you can see, quite purely topological. Here is the Euler characteristic of the Agbulut quark, and here are known Chern-Simons invariant of the sigma 257 and the direct sum, connected sum of two Poincare spheres. And but the derivation of that formula is quite lengthy. But we have published this. It takes 20 pages, but it is precisely this formula. But the manipulation was really cumbersome, and it is precisely the measure of the curvature of exotic R4 embedded in such a manifold, which is a kind of blow-up K3 surface. But it can be precisely derived such formula, and from that, using using the Hubble constant like this, we have quite physical value of the cosmological constants. So again, topology, only topology and exotic smoothness of our K3 surface determines such a realistic value of that thing. Okay, let us turn to the alpha parameter in Starobinsky model. Here is again the action, and we have such formula for deriving the alpha, and from the first topology change, we precisely get such a rough approximation, which is 0.6 multiplied by this precisely, which is exactly because the upper bound for alpha from experiment is 10 to minus 5. We get 0.6 multiplied 10 to minus 5. Again, purely topological expression. Also another cosmological parameters like spectral tilt is quite well fitted to experiments, but here is purely topological, is here, and another is a tensor scalar ratio, which is also very good agreement with Planck mission. What about phi, field, Inflaton field 5? Does it have any topological interpretation? It should have. So it happens that such interpretation is given simply by, well, maybe not simply, but by embedding of Chern handle in the first and second topology change. So the function describing embedding Chern handle, more precisely, first we embed two-dimensional surfaces which belongs to Chern handle, then into three-dimensional manifold. Then we derive such a Einstein-Hilbert action on sigma on our homology tree sphere. Here is mean curvature, and here is three-dimensional metric. And then we extend to 4 dimensions such an expression, and we get a big phi field, which is 4-dimensional, is a fermion field, and then we get a 4-dimensional expression for the action on boundary. And after conformal scaling, we get this conformal term. And here appear phi, which is precisely that phi which appear in the action of Starobinsky model. Everything, when you calculate what you want, for example, this is a reheating factor, which is the absolute value of h. From our calculation, it is purely topological. It is here, and but from experimental upper bound of given by Ellis, for example, you have such. I miss that value with previous 10 to minus 5. Here is 0.6. In the previous it was 0.7 something, but it's fit pretty well in experiments again, and it is what we can measure. But in fact, nobody can give such recipe how to calculate it. But here we can calculate many such things in one model. We don't know what that means, but we just show the result. Okay, the model which I presented derives many physical parameters. It is based on smoothness of K3 surface. Spacetime is embedded into exotic K3, and gains also modify smoothness. It is a classical structure. Smoothness is a Riemannian curvature, we would say. But derived parameters bear quantum mechanical origins. So the question is, why such a classical embedding produce something which is connected with quantum mechanics without direct referring to quantum mechanics? And it is not that surprising, because in some from other side we know that in fact non-standard smoothness on K3 surface leads to quantization in space-time. So how it happens? Simply this tree sphere, which I used in the calculation with radio of Planck length, from topological reason has to be widely embedded tree sphere. It is normal tree sphere comparing to the homology tree sphere, which are not normal, but it has to be widely embedded. But as being widely embedded tree sphere, there is the result of Kohn. From such embedding, we can generate the factor 3-1 von Neumann algebra. And this is the roots of quantum mechanics sitting in this classical picture. And in fact, we have shown also that precisely this 3-1 factor for Neumann algebra can be obtained as a deformation quantization of some classical Poisson algebra. Moreover, when the smoothness of K3 is taken to be standard, this sphere is tame, is not widely embedded, and this sphere is also normally 3-sphere. So we don't have any these cobordis, any such cobordis. Everything is just S3, 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 trivial. Everything is trivial. Only because of exotic smoothness we get these numbers and these results, which are purely topological. It is worth mentioning that everything can happen only in dimension 4, because only in dimension 4 we can find such smooth structures which realizes these things. Especially exotic R4 exists only in dimension 4. Thank you very much for your attention.
What about the signature of the metric? Do you have Riemannian metric or Lorentzian metric?
Essential question, yeah. I didn't tell about this because it's, okay. During the embedding, we forget about signature. Then we embed R4, Euclidean R4, which is Riemannian, of course. And also, but after that, signature, Minkowski signature appears from that fact that the end of R4, any R4 exotic also, for example, we have R4, let's say exotic, the end of this, let's remove one point. The end of this is which also is exotic. So in the Friedman terminology, we can use such a theta which depicts the homology sphere, which generates such as exotic smooth structure. And this is also the cosmological model. One can write down Friedman-Robinson-Walker equation on these things. So the story is, we use, at the beginning, we use Riemann metrics. But at that point, we cover Friedman-Robinson equation with this Lorentz metric. So this, but also the same discussion we had with referee our calculations. It's not a trivial point.
More questions? If not, I have one. So we are in this fortunate or unfortunate situation, but the fortunate that we have plenty of exotic structures in 4 dimensions. So, and obviously, in your approach, I would say that we argue that this choice is proper a posteriori, in the sense that because it fits to the numbers which we observe, okay, in nature. But you can you also say something whether some of the structures are a priori better than others? This would be some contribution to Mariusz' questions from yesterday. So why we are in this? Why our universe looks like it looks? It really looks like. So it means that I would say, okay, this is also somehow to argue, but there will be some argument that we should choose these models and not those models. Okay, so.
Yeah. So our approach is not very inventory in this context, because we chosen the best known structure and try. Maybe not so directly, but we have tried to do something with first the best known structure on K3, generated by the sigma 257. Other, almost you can take other homology tree sphere, but the result don't fit well to experiments. We didn't check everything, but we know it is true, such statement. Okay. Also, Mariusz yesterday told that we can consider, in principle, wider environment for our space-time, for our cosmological cosmology, which we know, which means that it allows such embedding in something which is bigger, but we don't know. I don't know what that means, but maybe there is some sense in thinking that our space-time is really embedded in a wider environment, but really I don't know what is the meaning of such a process. It is just a kind of procedure which gives results. But after this, we start thinking what that means. We don't want to give too quick answer. We just want to spend some time considering that situation.
In a sense, you are in the position to have to investigate each model and then decide whether it fits to the data or
yeah, but we have good arguments at the beginning that this is the only chance to get so many numbers.
Okay, so this was the answer I would like to hear. Okay.
What I'm going to say is not against your approach, but rather it expresses my internal feeling. It's too good to be true.
Yes, I agree. I agree. It's really a surprise to us. I don't say anything about this. What is the meaning? But it is too good. I agree.
You mentioned this relation to the type 3-1 Neumann algebra, which
Yes.
occur quite generically in quantum field theory. But can you describe how this is related to this exotic smooth structure?
Yes. So the point is we find some foliation inside the exotic smooth structure, and in Kohn's Moscovici description of factor 3, they showed that there is generator, one generator for such a algebra, which is connected with God beyond very invariant of the foliations. It is probably Elon Moscovici did it. I don't remember now, 2005. And what is this foliation? And we showed that in some radial family of exotic smooth structure, which is continuum many of them in standard R4, you have a relation between the radii, which is the number, and God beyond very invariant, which is also the number. And we constructed this relation. So the radial structure of continuum many, the radial family of continuum many exotic R4 embedded in R4, it is a well-known construction in topology, relates to foliations, such that a kind of invariant can be assigned to every exotic R4. And from that foliation, and from the result of Moscovici-Kohn, maybe, we have that this God beyond very invariant is the generator of the factor 3, one of the generators. So this is not very direct. We tried also to make direct approach to this, but it failed. It is not invariant. You can find in some case, but it is not invariant. So when you change some numbering, it changes. It is not a good correlation. But what I said, it's the way how we think about this.
Okay, and I have another question. All the numbers that you are fitting are actually functions under the renormalization flow. So what happens to the embedding? Is the embedding changing under the renormalization flow, or what?
Very good question. I really didn't mention that. The point is the sigma 257 is a hyperbolic manifold. So we have Prasad most of rigidity. And because of that, you don't have scaling. And the numbers are correct. We simply use the minimal Chern-Simons invariants. But the numbers are really fixed. Because of that, also four-dimensional discoveries. Functions in what sense?
They change with energy.
The function of embedding, yes?
The function, well, when you say the mass of the X, the mass of the masses, the parameters of the standard model, they are functions of the energy. Now, conventionally, they are at the experiments, so they are usually at the masses.
Yeah. Yeah, okay.
One possibility is that your embedding is changing.
Yes.
So there is a scale of the embedding, which is the scale at which you do the experiment or something like that. There's the scale of the renormalization.
Yes, the answer to that doubt, which is important, is the interpretation, what we think about that embedding, about this wider environment. Is this any absolute sense, or it is only temporary? I don't know at the moment.
Okay, so thank you very much. So let's thank all the speakers of the morning session. And as far as